All right, folks. Welcome. Are we back on the regular schedule now?
I believe so.
Because I thought the bell rang early last hour. I'm just gonna. Okay. Okay. So the question. A car in neutral does not move because no forces are acting on it. Is that true or false? False. 100% false. Just because something isn't moving doesn't mean there's no force acting on it. You've got forces acting on you right now, even though you're holding still. You got gravity and you got normal force. So this is an untrue statement. The answer is no. Okay. This is probably the most important lesson that you guys are going to get so far this year, because it lays the foundation for everything we're doing in the next month or two. And I'm just going to tell you right now, if you have questions as we go through this, you need to ask them, please. Last hour I got through just about everything, and nobody had any questions, and at the end they were like, I have no idea what's going on. So you got to let me know if I lose you, because if you have a question on something, chances are everybody else does too. So please don't feel bad about asking a question as we go through this. The more you're able to keep up with it, the better shape you're going to be in, and the better shape your classmates are going to be in. So, without further ado, let's get going on a very important section of notes today. You're going to label these notes vectors. That's right. They have direction and magnitude. So vectors, as mentioned, have a direction and a magnitude, and forces are the same way. If you've got one force going in one direction, you could also have another one going in a different direction. So you have to take both the magnitude and the direction it's going into account. And that's something we'll be doing at length today. Force is measured in newtons. And there are two particular forces that we have to point out for our discussion today. The first one is force of gravity. That's Fg. We've dealt with this before, but we haven't really said what the equation for it was yet. The equation for force of gravity is mass in kilograms times a value known as g. And that g value is different based on what planet you're on. If you're on Earth, it's 9.8. So for all practical purposes in this class, that's the equation. 9.8 meters per second squared is the gravitational acceleration on Earth at its surface. So that's where the g comes from. So in order to get force of gravity, you just got to take your mass in kilograms, multiply it by 9.8, and you're good to go. Force of friction is another important one, and that's what this little guy is. Again, if you want to just put a little F there, that's fine too. And force of friction is equal to something known as the coefficient of friction times normal force. Now, if you're on a flat surface with nothing pulling up or pushing down, normal force is just equal to force of gravity, so that would make it easy to deal with. But that can be a little bit more complicated, as we'll see today. Now, this would be if the object is moving. If the object is not moving, your force of friction would be equal to the same equation, but remember we call that static friction. So instead of just being the regular coefficient of friction, it would be normal force times the coefficient of static friction. And so, same equation, but if you're not moving, you'll just be dealing with a different coefficient of friction. It would be a little bit higher than the other one. So questions on anything so far? Everybody's good? Good. All right, moving on. No! Yeah, you'll have to watch the video, Andrew. We got to keep going. So, you guys all like math, right?
Yeah.
Yeah. Do you guys prefer algebra or geometry? Everybody says that. I like geometry way better because I like shapes. But yeah, most people do say algebra. We're going to be dealing with shapes in this class a lot. So, you guys ever heard of SOHCAHTOA?
Yeah.
Okay, good. You'll be dealing a lot with her. And we'll just go through a quick review on what SOHCAHTOA is, because we need that for what we're going to be doing today. So if we have a little triangle right here, this is the opposite side, this is the adjacent side, and this is the hypotenuse. And SOHCAHTOA just tells us how to relate these three sides of the triangle. The sine of the angle is equal to opposite over hypotenuse. The cosine of the angle is equal to adjacent divided by hypotenuse. The tangent, which we won't really be using too much in this class, is equal to the opposite over hypotenuse. And that's just how you get those different values. So, hopefully this is review.
Oh wow, I forgot about all this stuff.
And that's just summarizing what SOHCAHTOA is saying over there. Everybody on board so far? Good. So SOHCAHTOA should not be too hard to deal with if you have these equations. That's what you need. But we're not just going to be looking at triangles and putting in numbers. This is all going to apply to physics somehow. And specifically, it's going to apply to our force diagrams. So I'm just going to go through a couple examples and show you how that's going to work. Say we've got a box here, and maybe it's being pulled up at an angle. If it's being pulled up at an angle, we're going to have to somehow use a force diagram in this problem. Anything that looks like this, or just about anything in this chapter, you're going to have to draw a force diagram for it first before you start trying to solve whatever the question's asking for. So I can start with my force diagram. What's one force? Gravity is straight down. What else? Normal force. Will normal force be bigger or smaller here? Smaller, because we're pulling up, so the table has to do less work, less effort, in order to keep that block from falling through. So normal force would be smaller in this case. And of course, we've got this pulling force. And what do we call a pulling force?
Tension.
Yes, tension force. And it's acting at a particular angle there. Now here's the thing. This tension force deserves a detension.
Oh, you saw.
Because if we want to make force equations out of this, we got to look vertically and we got to look horizontally. Is this going vertically or horizontally? No, it's doing a little bit of both. And that makes our lives a little bit more difficult. Because in order to make these force diagrams, we have to specify what's going exactly up-down and what's going exactly left-right. So here is what we have to do with this tension force. We have to figure out how much of it is acting to the right. I would call that FTX, the tension force in the x direction. I also need to figure out how much is going straight up. I would call that tension in the y direction. Again, the reason that we have to do this is because when we're creating these force equations, we're dealing with the vertical direction and the horizontal direction. So we have to find out how much of this force is acting horizontally and how much is acting vertically. And that's where these arrows come into play. You can probably guess that's where SOHCAHTOA is going to come into play. So, if I wanted to figure out, say, tension in the x direction, this is the adjacent side, and typically you'll be given what the actual tension force is. So we'll have the hypotenuse. So do we got to use sine, cosine, or tangent if we're looking for the adjacent and the hypotenuse? Something with those two pieces of it.
Cosine.
Cosine, yeah.
Yeah.
Because cosine is equal to adjacent over hypotenuse. My adjacent side is FTX. My hypotenuse is FT. And that would be my equation. So if I want to figure out exactly how much of this force is acting horizontally, I just have to isolate my tension in the x direction in the equation. And in order to do that, you just multiply both sides by the tension force. That's how that works. The y direction is similar. The y direction, we're looking for the opposite side. So we have information for opposite and hypotenuse. Do we use sine, cosine, or tangent? Sine, because sine is opposite over hypotenuse. That's how that works.
Will there be numbers to plug into that?
Yes, and we'll get to those examples in a little while. Questions on this? Is everybody still aboard the ship?
Yeah.
This is very important. Okay, I'm glad to hear that. Nobody is overboard. So if I wanted to put this information in, say, a force equation looking vertically, here's how it would look. Vertically, we've got normal force and we've got tension in the y direction, both going up. Going down, we've got gravity. So the equation in the y direction would simply be normal force plus tension in the y direction minus gravity equals 0. Because these two are going up, gravity's going down, so we just take whatever's going up and we subtract whatever's going down and set it equal to 0. And that's how that works. Okay. Time for another example.
So is what's going up always going to come first?
Yeah.
us to find like the middle of it, the y of it.
What?
What is the fn plus fty minus ft? Like, what is the equal 0?
So the 0 simply means that this object is not accelerating up or accelerating down. Yeah. For this chapter, all of our equations will be equal to 0.
So we wanted to start at like base level, what you're saying? Like that's where it is.
Yeah, it's a way to put it. Yep. Next example is going to be kind of similar. The only difference is instead of having a force that's pulling this object up, we're going to have a force that's pushing it down. So maybe we've got a force that's acting at some angle, pushing this object down. We'll just say this is, looks like about 30 degrees maybe. And we just do the same thing. So for our force diagram, we've got gravity going down. We've got normal force going up.
Hi, sir.
Hi.
Can I just get one phone real quick?
Yeah, sure.
I'll be back in a minute.
So in this case, normal force is going to be here. Will that normal force be bigger or smaller than gravity?
You just said I'll be back with you. Oh, for real?
Yeah.
Then maybe. What?
Will normal force be bigger or smaller than gravity in this case?
Bigger.
Bigger, because we're pushing down on this object. And if we're pushing down on it, that table has to provide extra effort, extra force to keep it from falling through. So normal force is going to be larger in this case. And we've got our arrow going down. If you're okay with how to draw this on your force diagram, that's great. I'm going to do it the long way like I did last time. What's that?
Now we have to do the tension. Right?
Well, there's no tension in this one. This is going to be an applied force because we're
That's what I
pushing.
meant.
Yep.
Because I didn't. Is that an arrow pointing to the box?
Yes.
Oh,
Yes.
I thought it was just a one line.
Yep. We've got, this is an arrow. So if I put my arrow going into the dot, like this is going into the box, that's one way to approach this question. But I cannot end my force diagram here. All these arrows got to be coming out of the little dot, not going into it. So we just continue this arrow through. And if you remember from math, this angle equals that one. And because we're pushing, this is an applied force. And once you get to this point, you can erase what you used on the left side there. So that's our setup. And once again, we have a delinquent force here. And that is our applied force, because it is not acting just horizontally or vertically. It's acting both. And so we got to figure out exactly how much of this force is acting down and how much is acting straight across. Yeah?
Do you like take points off so you don't erase that other half?
No, that's okay. But I mean, it's a good habit to get into. Otherwise, your force diagram can get kind of messy. So we got to figure out the applied force in the x direction, FAX, and we got to figure out the applied force in the y direction, FAY. And these two forces are the ones that we're going to use in our force equation. Yep, Fax and Fay. Married for many years. And we approach this the same way we approached the last one. So if I want to figure out what's going on horizontally here, like you said before, we got to use cosine. because that takes both the adjacent side and the hypotenuse into account. And so we isolate the applied force in the x direction by multiplying both sides by the applied force. And that's what's going on in the x direction.
Would we know the length of the applied force?
Usually that'll be given to you.
Okay.
Yeah. In the y direction, then, it's the same thing, except we're using sine instead of cosine.
Let's go. So does it like get harder from here on? Today at least?
Well, yeah, I mean, this is the foundation. If you're okay with understanding this, then you're in really, really good shape. We're going to apply this to a specific problem in the next example. Question, Jax? No, that's fine.
When it goes like to the applied force, isn't that the hypotenuse?
This one? Yeah, this is the hypotenuse right here. Yep. So like sine is equal to opposite over hypotenuse. So there's your opposite side, and that's your hypotenuse. FA would be right here. Maybe this kind of looks like FA is the vertical one. Maybe that's clearer. Other questions so far on this? If you can understand this, you're in a really, 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 really good place. Yes?
Are we just trying to find the vertical and the horizontal?
Mm-hmm. Because once we find those, we have a pretty simple force equation that we can work with, just plus and minus. So like in this case, if I'm looking vertically, I've got normal force going up. Let's see, this is in the y direction. Normal force is going up. Going down, we've got gravity and applied force in the y direction. So you're going to subtract both of those things. And if you're a person that doesn't like parentheses, another way of writing this would just be they're both the same thing. You're just distributing the minus through. You're going to have a negative in front of anything that's going down. That's the idea. Yeah?
Why is it the y?
Because x would be the applied force in the x direction, and whatever's going opposite that, which is usually friction. We'll be dealing with that in the next example. Other questions on this so far?
Can you say that again? How you got that equation?
Sure. So when we get our vertical equation, we're looking at all the forces going up, and we add those, and we subtract all the forces going down. So we've got normal force up, that's the positive one, and we've got two forces going down, applied force in the y direction and force of gravity. So we're going to subtract both of those from the normal force. So it's normal force minus the combination of those two going down, and that equals 0. Other questions before we go on to an actual example here? Is everybody still on the ship? Sort of, okay. The thing with these kinds of problems is that, like anything else, it takes practice and it takes experience dealing with these until you're actually comfortable with it. So it's not like we're going to be doing this for one day and we're going to make it super difficult tomorrow. most of the stuff that we do with force diagrams that's complicated with angles has its basis right here with what we're doing right now. And we will be practicing this more over the coming days and weeks. So this will be an example of the sort of thing that you would see on your homework going forward here. This is an arrow there. So there's a force pushing into this block at a 20-degree angle. We'll say the block is 15 kilograms. We'll say the applied force is 100 newtons. Furthermore, we'll say that this block is not moving. It's holding still. You can see now we're going to take some friction into account here. So we just got to go through this using the same process that we've done in the past. Start with our force diagram. So gravity is down again. Normal force is going to be up. And just like the last example, it's going to be larger because we're pushing down on this object. So the table, or whatever it is that it's resting on, has to provide extra force to keep it from falling through. And we've got our applied force coming down like this. I'll just draw it in. And the angle is 20 degrees. Now, because it's not moving, we've also got friction here. And that's going to be acting to the left because friction always opposes the direction the object's trying to move. So it's trying to move to the right. Friction opposes it by pushing to the left. So there's our force diagram. Thank you. Now, typically, for these kinds of questions, they'll ask for two things. A lot of times they'll ask for what is the force of static friction and what is the normal force. These are common values that they want you to solve for. So, yes, this is still notes. So force of static friction. If we want to solve for this, do not resist the urge to go to the equation that just says mu times normal force, because we don't know the normal force. In order to solve for force of static friction, and in order to solve for normal force, what we need to figure out what's going on vertically and what's going on horizontally with the force diagram. All these problems are going to follow these steps. Mu s, force of static friction. Always begin with a force diagram, do a force equation, and once you have your force equation, you'll be able to solve for these things, as you'll see. Don't try to do any shortcuts. They won't work. So, let's say we want to figure out the force of static friction first. In order to get there, we have to figure out what's going on with this applied force, because it's not acting horizontally, and it's not acting vertically. It's acting both those ways. So this would be my applied force in the x direction, and this would be my applied force in the y direction. We're going to need those two things if we're going to solve for normal force and force of static friction. Any questions on the setup so far? All right. So if I want to solve for force of static friction, I'm not going to just put it into an equation. What I am going to do is I'm going to look at what's happening in its direction. It is a horizontal force, so I want to start with a force equation that is horizontal. So I've got applied force going to the right. So in the x direction, I've got applied force in the x direction. Going left, I've got static friction. And that equation will be equal to 0. It's at rest after all. And hopefully you can kind of see how we're going to go about solving for that force of static friction now. What are we going to do?
Find the X.
Yeah, we're going to find the x. We're going to find the FAX. If we can solve for the applied force in the x direction, it's going to be equal to our force of static friction. If you want to think about it in this equation, it's like just chucking this force of static friction over to the other side. Applied force in the x direction is equal to the force of static friction. So my job now is to solve for the applied force in the x direction, which is what we've been doing all class period long. Yeah, there's our triangle. So applied force, that's 100. I'm going to throw that in. So it's the adjacent side, which means we're going to use cosine. Yep, divided by 100 newtons. So to solve for it, you just multiply both sides by 100. Welcome back. So 94 newtons is what you should get if you plug this into your calculator. And when you do plug it into your calculator, make sure you're in degree mode. We don't use radian mode here. Questions on this?
So the static friction would be that as well.
Exactly. So 94 newtons is equal to your force of static friction. Okay, so we've got one more step to do here. We got to figure out the normal force. So let's see where that takes us now. Last chance. Any questions on the x direction and what we use to get force of static friction? Yes? Say that again? Because we have information about the hypotenuse, and what we're looking for is the adjacent side. So cosine is the only function that has both of those inside of it. Okay, so now we're going to do basically the same thing with the y direction. This one does get a little bit more complicated than the x direction, though. We're going to use green. In the y direction, we've got 3 forces instead of 2. So normal force is going up. Going down, we've got applied force in the y direction. And I usually put it in parentheses. Applied force in the y direction. And gravity is also going down. And again, you could say normal force minus applied force in the y direction minus force of gravity. If you don't want to deal with the parentheses, that would be just fine. You'll get the same answers. So if I want to solve for normal force, what I do is I just look at this equation. If I want to figure out my normal force, I just got to get all the other junk over to the other side. So if I move this whole thing over there, I find that my normal force is equal to FAY plus FG. You see how we go from here to here? So now, we just got to solve for both of these. Force of gravity is easy. Let's do that one first. Remember, force of gravity is just mass times 9.8. So that's just going to be 15 kilograms times 9.8. And you'll get some number for that. FAY is the more difficult one. So if I want to solve for the applied force in the y direction, it's the opposite side of my triangle here. It's opposite the angle. So for that, I got to use sine. So sine of 20 is equal to opposite, which is the applied force in the y direction, divided by the hypotenuse, which is 100. And so you can solve for the applied force in the y direction by multiplying both sides by 100. Now, I didn't calculate this number and this number separately, but I know that when you take this product and this product and you add them together, you know, this goes in for force of gravity, this goes in for applied force in the y direction, you should end up with 181 newtons. And that's your normal force then. So that's how this all works. Final questions. I know this is tough stuff, especially when you see it for the first time. But just remember, even though it looks overwhelming here, I mean, if you took a snapshot of this and you were like, this is what we're taking notes on in physics, you'd probably feel pretty overwhelmed just looking at that. But we're going to be talking about this a lot over the coming weeks, and you'll get more and more practice with it, and you'll get more and more comfortable with it too. So, as far as worksheet number 2 goes, for Monday, I'd like you to at least complete the front side. Basically, here you're just doing practice with sine and cosine. The back side, if you feel comfortable, go ahead and jump into it. Otherwise, I'm going to give you time in class to work on the back side here.